All right, Sophia, I forgot to start this, so I'm just going to give you the rundown real quick and check the slides out. But we just looked at these formulas, and now we're going to find the mass of this guy. All right, so what did you guys do to find the region of integration? One way to do it is to try to make equations for the lines. That often makes things easier. So for instance, this line is y equals 3 minus x. This line is y equals 0. This is x equals 0. And so you could go from, say, x from 0 to 3, y from 0 to 3 minus x. Okay? You could have also done the other way. You could have done, this is also x equals 3 minus y. So you could have gone y from 0 to 3, and then x is from 0 to 3 minus y. Okay? But I think I like the first one better. I'll stick with that. All right. So then you put in the density function. And in fact, I'm going to write it in a way that's easier to integrate. Okay? Now let's solve it. Go ahead. Yeah. So for the outside integral, you're looking at the absolute minimum, absolute value, absolute maximum values of x. So 0 to 3. But then for the inside integral, you're looking at where my y's going between. And y is going between two equations, y equals 0 equation and y equals 3 minus x equation. Okay. So 0 to 3 minus x. So naming the equation with lines helps you with your bounds of the interval. I have no idea how ugly this interval gets. Let's find out.
Doesn't work very good.
All right.
So we don't. Yeah, because it goes, okay. Basically, I just did these calculations. And then you know, there is your. Oh, well. Give up. Oh, wait. That's the interval that's all. They can solve any equation.
All right, I'm gonna start doing it up here. Yeah. Oh, gold star. I totally forgot about that. This is like doing math in front of other people is always terrifying. Yes, great job. All right. So here we go. Now we're on the right track. Let's combine some guys. Yes. So then right. So I can move that square root inside and get like a 3x minus x squared to the 1/2. Things that have the same exponent can be combined, right?
Oh, that's actually right.
And then we're close to a U substitution, but not quite. So what will we need for that? We would need a 2x on the outside. So let's just do that. So let's get 2/3, 0 to 3. So like if I wish I had a 3 minus 2x times 3x minus x squared to the 1/2. And then let's I don't want to change that. I want to change, what do I want to do? I don't want to add subtract the 2x. I want to add and subtract the 3. Yeah. So let's do like a 3/2 minus x. Um, well, what the heck? Let's just move the 2 in. Sorry, and get, no, it's doing too many things at once. I'm gonna mess up if I do too many things at once. All right. 3/2 minus x, and then I'm missing another 3/2 times 3x minus x squared, 1/2. Okay. So what did I just do? I said to myself, this is almost a U substitution. In order for it to be a U substitution, it would need to be like a 3 minus 2x. Right? But I don't have that. So I can either like subtract and then add a value of x. Or I could like split up the 3 into 3/2 here and a 3/2 there. Okay. Once I have a 3/2 here, this is the U substitution. So just if I move the 2 in here, it becomes a 3 minus 2x. So I'm ready for U substitution right here. Here, I would want to do completing the square and then an arctan. Okay. So let's do it. So I'm moving the 2 in. I'm moving the 2 across everything. 0 to 3. 3 minus 2x. I need the 1/3 there. Times 3x minus x squared. 1/2. Plus 3 times, I need to complete the square inside here. So I need negative x. Negative x squared plus 3x, and then 3 divided by 2 is 3/2. Squared is 9/4. So then minus 9/4 plus 9/4 to the 1/2 power. And so then I've got 1/3, go from 0 to 3, 3 minus 2x times 3x minus x squared to the 1/2 plus 3 times, I'm gonna switch the order and do, get out of here, you're in the way. 9/4 minus x minus 3/2 squared to the 1/2. Okay, so I'm doing many algebra steps at once here. So if anyone's getting lost, please raise your hand. Um, so here, I've got a completing square situation. I've just got all the opposite signs of what you normally see, right? So that means it's a minus, and then if you change all the signs, then that's a minus, so that would be a 3 minus 3/2 squared, right? So if I were to FOIL this out, I would get, and then move the negative through everything, I would get this. Okay? So now I've got square root of, oh, but arctan is when you have 1 over the square root of. So this is oh, this is like when we were doing arc length, right? Yeah. And so we already know this is a thing we already know, a formula we already know, right? So recall, I didn't leave any space for this. Recall that like when you integrate the square root of x squared plus a squared, that's going to equal, I didn't give enough space here either. That's going to equal 1/2 natural log of, yeah. So is it like, was the natural log only for part of it? Yes. Um, it was 1/2 times x squared, x times the square root of x squared plus a squared, plus natural log of x plus square root of x squared plus a squared. And there's like a 1 over a in there somewhere. Yeah, let's look it up. It's in the integral tables in the back of your book. There's no reason for us to rederive it. We derived it once in class. Once is enough. Okay. Involving trig. Okay. Yeah. Um, yeah, I almost had it. You were right. It has a squared on the out. Oh, where did I go? It has an a squared on the outside of the natural log. A squared natural log of u plus a squared plus u squared. Yes. Okay. So then right here we have let's see, so 1/3 times, and then we've got u substitution. So this is like, that's a u and that's a du. Let's just change this. So this is a u, and that's a perfect du. And so then I get u to the 3/2 times 2/3, and u is 3x minus x. So the u is 3x minus x squared to the 3/2, and then plus 3/2 times x minus 3/2. That's my u. So now that's u, and that's a squared. So a is 3/2. So x minus 3/2 plus the square root of, wait, there's a minus in there. That's different. A squared minus U squared. A squared minus U squared. Oh, it's arc sine. Okay. So it's we're still going fine. So it's still 3/2 times so I'm on page 901. U over 2. So U is x minus 3/2 times square root of 9/4 minus x minus 3/2 squared. And then plus 9/4 times arc sine of U over A. X minus 3/2 over A. Okay. From 0 to 3. So I don't know what you guys are whining about. Okay. Did anyone get any numbers?
Magnitude of a problem.
Low.
Zero.
Greater than 0, but low. I don't have that sort of closeness to that. All right. So I'm out of space, which is just hard. All right. So if you plug in 0, is anything anything? Oh yeah. Yep.
3/2.
3 pi over 2. Yeah. Yep, the middle term is something too. Yeah.
And you square it instead of just zero.
Oh yeah. So the square root would be 0. Yeah. So just the last term. But if we plug in 3, we've got like if we plug in 3, the first term is also 0 because we get a 9 minus 9. We plug in 3 there. We get the middle term is also 0, right? Because 3 minus 3/2 would be 3/2 squared. So then if we plug in 3, so the first two terms are 0 for both 0 and 3. And so then plugging in 3 there would be arc sine of 1. And so arc sine of 1 would be pi over 2, right? What's that? So we'll get 9 over 4. We'll get 1/3 times 9 over 4 times 9 over 4. Arc sine of 1 is pi over 2. And then minus 9/4. Arc sine of -1, which would be 3. You could either be 3 pi over 2 or negative pi over 2, depending on how things are. I think in this case, it's the negative pi over 2. And so that means that this is equal to, so the 1/3 goes through, and I've got 3/4, 3/4 times pi over 2. 3/4 pi over 2 is basically 3/4 pi. 3 pi over 4. See? What were we whining about? All right. Now, that was one of them. Now, let's find the two moments, no, the centers of, what are they called again? Centers of mass. Um, yeah, the moments. Given how this is going, I'll do it right up here too. Okay? Is everyone okay with that? And maybe we'll just skip to the next one. I don't know. This is not, it was ended up being a little harder than I thought, even though this is mostly what we're doing, just lots more practicing now. So how much uglier are these integrals if we have an extra x or y in there? Now, there's one nice thing. You know what one of the nice thing is? So when you're doing these problems, work smarter, not harder. How can we work smarter, not harder? If we look at what sort of symmetry does this guy have? What sort of symmetry does my shape have? If I swap x and y, is it the same shape? If I swap x and y, is my density the same? The density and the shape both have x, y swapping symmetry, which means I only have to calculate one of this of these guys, of these moments of inertia. Okay? So, pick your poison. So 0 to 3, 0 to 3 minus x, 0 to 3, 0 to 3 minus x. And so then we'd have x to the 3 halves, y to the 1 half. All right, so this will be my. We'll calculate my. All right, dy dx. And so we might have to go through the whole rigmarole again. I don't know. So, um, so then 0 to 3, integrate with respect to y, and we get x 3 halves, y to the 3 halves, times 2/3, from 0 to 3 minus x, dx, and then move the 2/3 out here, 0 to 3, and then we've got x to the 3 halves times basically 3 minus x times 3 minus x to the 1 half. And so really you could think of x to the 3 halves as x times x to the 1 half. So we can combine like powers, and that would give us, combining like powers would give us 0 to 3. I'd have a 3x minus x squared, and I'd have a 3x minus x squared to the 1 half power. So then what have I got here? What can I do with this? What to even do with the x squared? Shoot, we might have to do integration by parts. Okay. Is there a better way? I don't know. How many pages do I have? Just one page. All right. Well, when life gives you lemons, um, what's our best option here? So last time I was able to break things into u subs. Here, no such thing. Because I have no custom. I mean, that x squared is the thing that's slowing me down right now. And the x squared is a perfect candidate for integration by parts, kind of lower it to something else. And as long as I'm lowering stuff, I can just lower the whole thing. So yeah. See. And let me just check real quick if there's anything that would be useful. Probably not. There's no like u to the 3/2 when you don't have the du, of course. Okay. So or I could do trig substitution. I'm feeling like doing trig substitution today. All right. So trig substitution means that we take our if I'm doing trig substitution, I'm just going to write it like this to the 3/2 power. Okay. That's what it is. So then whenever I've got stuff like that, if I were to put like, oh no, that's going to be ugly too though. Because you want squared terms. You want the difference, addition or subtraction of squared terms for trig substitution. This is not good for trig substitution. Okay. So you guys get to see me in my problem solving mode. Let's try. Thank you, gold star. Yeah, let's try integration by parts. So then if I'm doing u equals 3x minus x squared, then du equals 3 minus 2x. And then if dv is 3x minus, no, I can't do that because I need, I want to take that power down, but this power is going nowhere. We'll just leave it be. All right. This is a application problem. Let me tell you something about life after Calc 3. In graduate school, I was taking a quantum mechanics course. And it was quantum mechanics basically means like one of the things about quantum mechanics is that you're treating every particle as a wave. Okay? So every particle is a wave, which means every particle is really a function. And so trying to find like the most likely place of the particle is about integrating like over several things. And so there was one problem on one of my homeworks where it ended up being a 9-part integral. But it was a physics class. And so I set up the integral. I did it in whichever software program I had handy, Mathematica, I think. And then I submitted my homework as like, here's the integral. Mathematica says the answer is this. And I got full credit for it. Because quantum mechanics is not grading you on your ability to do a 9-part integral by hand. It's grading you on your ability to do quantum physics, right? And similarly, life after Calc 3, like there's a lot of things in math where everybody should be forced to do it at least once. And then after everyone's been forced to do it once, everyone can use the shortcut. Does that make sense? It's like a initiation, but it's more like you should know how it works before you just integration machine goes buzz, Okay? So basically you guys are almost done with Calc 3. Okay? And when you start, whenever some of you are gonna go on to actual science or engineering, things like that. And when you, like we, at this point, we have set up the integral. The integral is set up. Once you have set up the integral correctly, the computer can do it. And then, like, if you're asking if I want to know the center of mass, like that's not a thing where it matters, like, integration techniques and all that. It's just like you just need a number. Okay? So we put this number in our calculators, and have any of you guys put this number in your calculators yet? This integral in your calculators? Not this one, like this guy right here.
Whoa, wait.
Yeah, but we need to.
Oh, it only stops at 40. I thought I could.
3.53? Yeah, Google it. Every calculator is different. Find the YouTube video. All right, which also, like on the final, I have picked out problems that don't go that crazy. And so I need you to show your work on the final. It's your last hurdle of like the initiation process. If you don't show your work on the integrals, I'm just going to assume you just put it in your calculator and you have no idea how to do it. Okay? All right. So 3.53. And then equals 3.5353. Okay. And so then 3.53 divided by 3 pi over 4. So we'll call this my equals that. M equals 3 pi over 4. And then it doesn't like, there we go. And so then m sub y divided by m is 1.5. Okay? So that means if you think about like y 0 less than y less than 3 minus x, or 0 less than x less than 3. How do you do this again? Maybe it's the other way around. There we go. All right. So for that shape right there, if you look at the point, 1.5, 1.5. No, that can't be right. We've done something wrong. Oh, that's because I put the 1/2 there. Come on, guys. Oh, I think we found m wrong. That's what little m is supposed to be. Yep. Okay. X to the 3/2, y to the 1/2, dy dx. Come on, what's wrong? Does it not like the my thing? 3.9. All right, can't I name it now? There we go. So then 1.125. So 1.125. Yeah, because they're symmetric. So then the balance is right there. Okay. The density is square root of x times y, so the density is much dense over here, not dense there. So it's going to be
And so that's the center of gravity.
that's the center of gravity. If you had a thing like this with the density of that function, it would balance right there. All right. Okay. Well, mass. All right. I learned my lesson and I've got an easier density function now. So now I've got a new thing here. I want to find the regions between the curves y equals x and y equals x squared with a density function of x in an interval 0 to 1. So draw the shape, draw the region, find the mass, find the moments around the x-axis and the moment around the y-axis, find the center mass. The region you should have drawn like that. Okay. So we're in that little sliver right there, which means m is going to be integral from 0 to 1, integral from x to x, no, x squared to x. X squared's on the bottom, x is on the top. Oh, I need to put this down so I have better. Of x dy dx. Which is a much, much easier integral than last time. You guys can do it. I believe in you. 1/12? Okay. So our little guy weighs 1/12 of whatever unit we're measuring in. Okay? So now, what is which one do you want to find? Um, yeah, mx or my? Let's do my. It won't be the same. We have to calculate all of them. So we're now calculating same limits of integration, 0 to 1, x squared to x of x squared dy dx. As the moment around the y-axis will be measured in x's. So you get an extra x. When you do the moment around y, you get an extra x.
Okay.
So the mass had x, so we just get a second x in there.
Um.
Let's also find the moment around the x-axis, which is when you throw in an extra y.
No, that is, oh wait, oh. You're right.
Right? What's the common denominator there? I don't know. That's 1/4 times 1/2 minus a third. So 1/4 times a sixth is 1/24. Okay. So that means where is the center? The center is basically x bar, y bar is going to be equal to, so x bar is my over m, and y bar is mx over m. That's going to be, so m is 1/12, so dividing by 1/12 is just multiplying by 12. That's 12 over 20 and 12 over 24. And so then 12 over 20 would be 6 over 10. So basically 0.6, 0.5. So, which by the way, our original calculation for my in that other problem, we were only off by 3/2, which means we just forgot a 3/2 somewhere. So we were basically there, just forgot a 3/2 because we were too messy. Okay, so the lesson there is don't be messy. All right, now let's take away this region and look instead at y's between x less than y less than x squared. Nope, x squared is in the bottom. X squared less than y less than x. And then we don't need to do anything with the, we don't need to show that point. And so there's our region. And then if you look at the point 0.6, 0.5, it's right there. And so that's where the thing would balance. Because it's density, it's a very weird density. Density was just x. So this is like nothing here, and it's most dense over here. Okay, so if it has this weird density function like that, it's most dense over here, so it's going to balance. Pretty cool, huh? Okay. I'm okay if we take most of our time on this section. It's not as much in the Jacobians. Yeah. Yep. So we're at an hour 15. If we've been in class already, let's take a 5-minute break, and then we're gonna do some 3-dimensional stuff. Okay, can I talk to you guys real quick?
He's like, this, I mean, you shut up and it's fine.
Oh.
What?
Remember the last one?
Yeah, but it's a motor.
Your car's better. You don't buy a car.
We can. Like, last week, we have a fine. We're approved to miss the California.
I'm not doing it. Well, you have to retake it anyway. Just take it anyway.
I'm gonna take my file.
You can take the file and go.
It's like.
You have to have a stopper. Where?
Take your finals like 2 days for the number.
I'll have to be there later, but stuff.
Oh, it's. Exactly. The dog going.
More than 4 years.
Well-
We have 100.
No, no,
So that's only 15 grand.
for, then almost student is 120.
Yeah.
For us engineers, it's 137.
Oh, okay, that makes sense.
But you also have to take, well, if you want to, you could take stuff over the summer.
But that's the graduating 4 years, so some people don't get that. But we feel something for. I don't know. Was that your turn for yours?
And it's so late.
Yeah.
I'll just.
I would rather-
Psych it out. But spending like $20,000. Okay, unless you literally fails.
What? Oh, you're sugar free?
Yeah, it says sin azúcar. I know what that means, without sugar.
I mean, I don't know. Is it totally?
Then that's good.
Like it's all like giving them out. I normally have
But you
coffee.
fail that,
But these are.
that's okay.
How did you do the last study with it? You just take an integral of the inside. And then just whatever that answer was, you
What's
Yeah. Was yours wrong?
after taking all these.
Well, one fall, I've been taking chocolate and back in the machine. I think it's
I'm working right now. For long. For now, great. I'm pretty well. I can't like. No, like I used to.
You keep this. We don't want it.
All right. So now let's talk about moments of inertia. So moments of inertia help like think about how a shape would rotate. Just because the place where it balances might not necessarily be the place where it spins. So you end up doing like the moment of inertia around the x-axis is y squared, and throw in an extra y squared. If you do it around the y-axis, that's an x squared. And if you're thinking about around the origin, then it's x squared plus y squared. Okay. And then for those of you who are actual science, you actually call these in probability theory, you call these second moments, and they're related to calculating the variation and standard deviation of continuous probabilities. Okay. Okay. So let's get to it. Oh, not this one. Nope, we're not doing that one. All right. Yeah. Let's go back up. Okay. Sorry. Yeah, a lot of like when you're doing around the origin, you're probably going to want to switch to cylindrical coordinates or polar coordinates since it's just a double integral. Yeah, gyration means spinning. So again, blame the Greeks. Like gyration is basically Greek for spinning. All right, so what's that?
I need to take some deep breaths.
All right. Yeah. Yep. Okay. So my example is going to be too hard. So let me pick out a homework question or something. All right. What are the homework questions I assigned for this section? Canvas, back, homework 5, 6, and 7. Nope. Pages. Front page. 5, 6. So I'm only assigning 4 problems. So 302. Yeah. 2-1. And then okay. There's 303, 30. And then what about 322 and 328? 322. Oh, that's why I was doing it. It was 323. Yikes. Okay. No, I'm not saying yikes about your homework. I'm just like, my example here is basically number 323, but with a different size triangle. Oh, but this is a better triangle. This is a better triangle. Okay, why is this triangle better? So it's a 45, 45, 90 triangle. But last time we had this triangle right there. And this time we have this triangle right, but there. And so, what does it mean to have that triangle? Think about like the equations of the lines. The main issue with our last triangle was that we had like a 3 minus x line, and that made everything awful. Okay? So here we have y equals x, y equals 0, and then x going from 0 to 2. So this is totally doable. So let's do it. So then let's find m. It's going to be from 0 to 2, from 0 to x of square root of xy dy dx. Let's find all 3 moments of gyration now. All right. I'm going to do it up here. Yeah, sure. All right, so how about we all do y first? So that would be 0 to 2, 0 to x, and you'd have like a x squared times x to the 1/2 would be x to the 5/2, y to the 1/2. An extra x squared because we're doing gyration. Mhm. 2 to the 4th is 16, 32, 64. Okay. Did everyone else get 64 over 15? All right. That's a good sign. Let's do the other one. I took the 2/3 out.
Oh.
So then we're doing 0 to 2, 0 to x, x to the 1/2, y to the 5/2. There's a shortcut I'm going to show you for the origin. Those are eyes, yeah.
Yeah, it's awesome. Love it. It's my favorite. I have a bright smile always when I'm in it.
I'll look over it sometimes.
Yeah, I'm always impressed.
Do this.
Oh, I'm just looking at the board. I'm just trying to stay awake. I like 4 days last year. Oh, I tried to do that.
I can't even believe that. That's probably where I just.
Yes.
Tomorrow that. Why ask me tomorrow? I know it's good. I know 100%.
Well, I can hold on.
Well, you're.
All right. So the beautiful thing about I0, so that's the integral of x squared plus y squared times the density. Well, that's going to be, what if you just split that up to the integral of the x squared density plus the integral of the y squared density? Well, that would just be iy plus ix. So we just need to add up 64 over 15 plus 64 over 35. Oh, gotta find common denominator. Oh boy. I'm gonna 7 over 770 plus 35 is 105 plus 64 times 5 over 105. So then that's 64 times 12. So then 64 times 12 is 640. 640 plus 128. 640 plus 128, so 768. 640 plus 128. Is it not right?
No.
Oh,
Put it. You can
Simplify it
put
down to
that-
128.
Oh, no, yes, it's simple. It just doesn't look like it would.
oh, because of the factor of 3. Oh yeah. Gold star. All right. So then 105 is is basically like 3 times 35, right? So then, this is just what do we got here. So 3 times 35. So then 64 times 4 would then be 128, 256. Is that right? Slow down, slow down. Okay. So 5 and 12 is 5 and 7 is 12. 105. Okay. But
35 times 5 is 175.
oh, thank you. Thank you.
I should work. 120.
Oh, then you need to multiply by 3 instead of 5 to get 105. Break it down.
All right. So apparently, it's too late in the day to do fractions. And so what did you guys get? 128 over 21. All right. So that means then that our like the radii of gyration would be like Rx is going to be Ix over m square root, right? And my m was 16 over 9. So this is the square root of 64 over 15 times divided by 16 over 9 is multiplied by 9 over 16. And so then there you go. Okay, that's just square roots of fractions, right? So we're good to go from there, huh? Now, we can also do this in 3 dimensions. And so it all works roughly the same. You call your moments y, z, because the moment around the YZ plane. The moment around the YZ plane, distance from YZ is x. So, and then the moment around the XY plane is z. So whatever letter is missing, that's when you're throwing in here. Okay? And then what your x bar is m from the one that's missing x. And your y bar is the m from the one that's missing y. Z bar is the one from the m that's missing z. Okay? So this is just applications of triple integrals, applications of double and triple integrals. And we're doing, this is all geared towards physics, but these are the same integrals work towards probability theory. Okay. These are in your book, and there's a lot of symmetry to these equations. So I'm gonna move on. All right, and then you get these guys. Now, these guys, now if you're in 3 dimensions, you're thinking about like around the x-axis, around the y-axis, around the z-axis. And so then you get these guys. And they don't add up as well. So you got to do 3 different ones. Okay? Do I have an example? So then for Ix, you put in the 2 variables that are missing, y and z. For Iy, you put in the 2 variables that are missing, x and z. For Iz, you put in the 2 variables that are missing, x and y. Okay? And these formulas are given on page 603 in your book. So we'll move on. So suppose Q is a solid region bounded by x plus 2y plus 3z equals 6 in the coordinate planes. and it has density x, y squared, z. Find the mass, the moments about the planes, the centroid, and the moments of inertia, and the radii of gyration. And that'll finish it for this section. So let's do it. Actually, let's talk about the region of integration as a class. How would I even find the region of integration? What's that? We're not going to find all these. We're just going to set up the integrals and call it a day. Well, and then move on to Jacobins. So how do I set up this integral? Yeah, the lower bounds are all 0. Okay, because this plane, think about the 3 coordinate planes, then this plane's intersecting them all like in the positive octant. Okay, just remember how planes, the vector that's normal to the plane is like 1, 2, 3. The vector that's normal to the plane is 1, 2, 3. And then you can pick points, say like 1, 1, 1 is on this plane. Okay, so this plane is like the normal vector of this plane is pointing in the positive octant, and then the point 1, 1, 1 is on this plane. Okay, so it's like we're talking about something in the positive octant. Okay, so where do I start then? All right, that's a good way to start. Okay, so maybe I could come up with some start. So x goes 0 to 6. Okay. 0 is the absolute minimum value of x. 6 is the absolute maximum value of x. Okay. You want to do y next? All right. Once I've chosen x, what are the minimum and maximum values of y? I think y is going to have a minimum number of 0. So then what's going to be the maximum value of y? And there's going to be an x in the top of this. 3 minus x over 2? Yeah. Okay. And then for z, we just solve for z in that equation, right? And so it'll be 2 minus 2/3 y minus 1/3 x. And then you throw your density function in there, x, y squared z, dz, dy, dx. Call that m. And then we've got we're not going to solve this integral because it will get ugly. But we will set up the other integrals. So how do I set up the other, how do I set up, say, like m y, z? Same thing, add an extra x in the middle. 0 to 6, 0 to 3 minus x over 2, 0 to 2 minus 2/3 y minus 1/3 x, x squared y squared z, dz, dy, dx. Okay, and then m xz. I'll just throw in an extra y value. So it's blah, 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 x, y cubed z. And then m yz to be the same triple integral x y squared z squared dz dy dx. What's that? mxy? Yeah, sorry. Thank you, Gold Star. Okay. Right? And then our centroid would be x bar, y bar, z bar equals m y z over m, m x z over m, m x y over m. Okay, once I've computed all those guys, I compute those fractions, and I have the middle point of the solid. Okay? And then I would compute things like I x. And that would be that triple integral. And then it would be x squared plus, no, y squared plus z squared times x y squared z. Right? And then I would compute I y. And that would be that triple integral with x squared plus z squared times x y squared z. And then iz would be that triple integral with x squared plus y squared times x y squared z. And then we'd calculate our different radii of gyration. And, our x would be the square root of I x over m, and our y would be the square root of I y over m, and our z would be the square root of I z over m. Questions about that? All right. Yeah, exactly. Okay. So now let's talk about Jacobians. A couple of years back when I was teaching this, some of my students were trying to convince me. So this is like when Heidi was pregnant with our son Benjamin, and they're trying to convince me that we should name our baby Jacoby. And I said, Jacoby Johnson, call him JJ. All right. So let's recall U substitution. So with Calc 1, no, well, is U substitution Calc 1 or Calc 2? A little bit of both. Okay. So when you're doing U substitution, you're really letting U be a function of X, right? And then du is going to be G prime dx, right? Okay. So basically you're defining like U is a function of X, and then U prime is just G prime times dx. Okay. So Things get stranger when we have to deal with how the dA changes. Okay? So you remember how the area of parallelogram, where you have the parallelograms given by like a vector and a vector give you two sides of the parallelogram. The area of that parallelogram is the cross product, and then the magnitude of that cross product. Okay? So that means that not only do we have like kind of the du and the dv, but we also have how the du and dv can be not perpendicular. Because x and y are perpendicular, but du and dv might not be. And so that's what we get with this term called the Jacobian term. Okay? And so the Jacobian term is like basically xu yv minus xv yu. And then you always do the absolute value around that when you're integrating, so that you get you don't end up with negative area. Okay? Yeah, so this is magnitude, so that should be absolute value there. Sorry. Okay, so we're getting the Jacobian term because sometimes our u's and v's are not perpendicular. And we got to account for that. And so that's where the Jacobian term comes in. Okay, so I'm going to walk you through this one. We're going to go do this integral of 4 over x minus y squared, where r is a trapezoid, bounded by the lines x minus y equals 2, x minus y equals 4, x equals 0, and y equals 0. So what does that shape look like? So then x minus y equals 2 would be there, and then there. Okay? So in that region. Okay? This is not a really great region to integrate because it's like you got like two parts. You have to break it into two parts, like there and then there. Or between here and there. Right? But we can do it all at once if we do a change of variable. Okay? So if we do u equals x minus y, and then say v equals, could be anything we want it to be. But why not like x plus y? Okay. So then, if we do this sort of substitution, then we need to solve in terms of x and y. We need to solve in terms of x and y in order to compute the Jacobian. Okay? How could I solve for x? If I add those two equations together, what would I get? 2x would equal u plus v. So then x equals u plus v over 2. Right? And then y, if I take the v minus the u, sorry. Then y would be v minus u over 2. Okay? And so then, I'm thinking about, say, x, u, y, v. So x, u, y, v, doesn't really matter. X, v, y, u. So I need to compute 4 partial derivatives. Okay? So the 4 partial derivatives are xu, xv, yu, and yv. So xu would be 1/2. Xv would be 1/2. Yv would be 1/2. And then yu would be negative 1/2. Okay? So then the determinant of like a 2 by 2 matrix is you multiply diagonal minus this diagonal. So we get 1/4. So we get top left times bottom right minus upper right times bottom left. So we get 1/4 plus 1/4 is equal to 1/2. Okay? And so then to do this integral, when we switch, if we switch this integral here to u's and v's, then I get an extra 1/2. Okay?
You say that again.
Yeah.
So you know how when you're doing u substitution and if like you always often end up with an extra number or something? This is my extra number. Okay? Because my u and my v are bigger than my x and my y. Okay? Because like x and y are u plus v over 2, y is x is u plus v over 2, y is v minus u over 2, u is x minus y, v is x plus y. So my u and v are bigger. So when I switch to u's and v's, this I need to also multiply by 1/2 in order to still get the same answer. Because you know how when you're doing your integral, this thing changed. Like, so this means the 1/2 means, this 1/2 means that dy dx equals 1/2 du dv. Okay, that's what the Jacobian does for us. So when we substitute into that integral, we get integral of 4 over u squared, which would be like basically 4 u to the negative 2. But then we'll also multiply by 1/2. So when we substitute for the dy dx, we get 1/2 du dv. And then the bounds of my integral. So this line is x minus y equals 2. Otherwise known as like u. U equals 2. Right? So u goes from 2 to 4. And then this line is actually I want to do u last, and you'll see why. Because it's so nice and numberish. Okay? U is so nice and numberish, I want to do it on the outside. So then V, so I'm going between like the bounds of my shape then. This line was x minus y equals 4, which translates to be u equals 4. Okay? This line was x minus y equals 2, which translates to be u equals 2. But I have other bounds on my shape, this line and this line. This line is basically y equals 0, right? So if y equals 0, that means, like, what is y? V minus 2 over, that means v minus u over 2 equals 0. Otherwise, it could be written as v equals u. Okay? And then what's this line? This line is x equals 0. So if x equals 0, then we're talking we're talking from, so x equals 0, that means u plus v over 2 equals 0, which basically corresponds to v equals negative u. So then we'll go from, this goes from negative u to positive u. Okay? And now I've set up an easier integral. Okay? Whereas this integral is not pretty. This integral is quite pretty. So we're good to go. Questions about that? Yeah. I chose them based on experience. Sometimes the book is going to tell you. So the first homework problems you have, I think the book tells you which ones to do. But basically, like, there's two things happening. You know to do something like this when you got these, so I've got these slanted lines where I've got x minus y showing up in my lines and in my inside. So whenever you have a weird thing that's showing up in your bounding lines and the inside of your integral, make that a u or a v. Okay? And then for v, I didn't have to do it this way. I could have done all sorts of things. Okay? Just had to be something that's not u. Okay? So this was the natural, that's kind of a natural guy to choose if you've got x minus y. Okay? It's late in the session, late in the day. We can do this. Okay? Now, the book lays out your problem-solving strategy because there's some choices here. It's not just in a recipe. You got to make some choices and some critical thinking. Okay? Always sketch the region. Okay? And then, like, what are the curves bounding the region? Always draw the region. Always label, like, what the equations are bounding the region. That's like what I did with the trapezoid. I drew the trapezoid, and then what are those equations of the curves bounding the region? Okay, so depending on the region integrand, choose a transformation. Like x is some u's and v's, y is some u's and v's. This is also in your book. You don't have to take a picture of it because it's in your textbook. And then determine the new limits of integration by the Jacobian. And the integral and the integrand, replace the variables to obtain the new integrand. So it's like integrand when it's talking about the inside of the integral. Okay, so and then replace dy dx with dx dy, whichever occurs by the Jacobian, and then du dv. Okay. Let me back up a little bit and think about, remember switching to polar, where we showed geometrically how you get an extra r? We can also show that algebraically now using Jacobians. Okay? So if x equals r cosine theta, and y equals r sine theta. Then if I make like x r x theta, y r y theta, then what is xr? What is the derivative of x with regard to r? Cosine theta. What is the derivative of x with regard to theta? Negative r sine theta. Then similarly, y with respect to r is sine theta. And y with regard to theta is r cosine theta. And so then you you do, oh dear, you do that minus that. What are you doing? Okay, so this is equal to r cosine squared theta minus negative r sine squared theta. So then that means we get r cosine squared theta plus r sine squared theta, right? Which is r times cosine squared theta plus sine squared theta, which is just r. Okay, so when you switch to polar, your Jacobian is r. That's the extra thing you have to multiply in when you change variables. Okay? And so then that means dx dy equals r dr d theta. Okay? That's what the Jacobian is all about. Now, I want you guys to do this one. So this is similar to a homework problem where I'm telling you exactly what to substitute. So then draw the region, label the curves of the region, and then switch everything to u's and v's. Find the Jacobian. Don't know what you're doing. Talk to your neighbor. Let's kind of break this into steps for our class. So step one, draw the region. And then step two, label the boundaries. So then relabel the boundaries using only u's and v's. think I have something wrong. Y equals square root of X. All right. How can we simplify the equation square root of u plus v equals 0? U equals negative v. Right? How can we simplify the equation square root of u plus v equals square root of v? U equals 0. Right? So it's better to put the simplified ones here. U equals 0. And then u equals negative v. And then this point right here also is at that point v equals 0, by the way. Right? Because v equals x. So the region of integration is then what? Mm-hmm. Well, since v is going 0 to 2, that means v is positive. And so we should put the negative v on the bottom. Okay. And so then but we're not ready to do the whole integral yet because we haven't done the Jacobian. So we need to do the Jacobian, which is going to be the determinant of x u, x v, y u, y v. So compute the Jacobian. Oh, I need more space. Well, y sub u is going to be u plus v to the negative 1/2 times 1/2. Yeah. So then it's going to be 0, 1, 1/2 u plus v to the negative 1/2 And then it doesn't matter there because it's by 0. So then you get basically absolute value of that will be 1/2, basically like 1/2 squareds of u plus v. And so when we substitute, y is the y is the square root of u plus v. So I'm substituting for y is square root of u plus v, right? And then sine of, I'm going to do this lower down. I need more space. I'll do it right here and then I'll move to the next line. 0 to 2, negative v to 0. And then I need to substitute y sine of y squared minus x. So then substituting, I get 0 to 2, negative v to 0. Y is square root of u plus v. Then sine of u plus v. And then x is minus v. And then the Jacobian is 1/2 square roots of u plus v. And then we get du dv. So how does things simplify? How does things simplify? Yeah, 1/2 sine of u du dv. So then look at that. You guys solved that. You know how to do it. Oh, you. Hmm. We're going to get a negative number, but that's okay because I think the original thing is negative. Yep. Okay. Um, yeah.
I'm trying to even function, could you change negative e to just be,
Yes.
it'd be positive?
Yep. And it does the same thing works out because sine is an odd function, so I can move the negative through and I still get, yeah. So either way, like that. And then -1 plus 1/2 sine of 2, and then -0. So there you go. Okay. So that's an example of using Jacobians. Okay. Now we can go 3D. So do you remember doing these determinants for cross products? Where when you're doing a 3 by 3 determinant, there's a slower way to do it, but the faster way is kind of what I showed you for cross products, where you copy rows 1 and 2. You go x u, x v, x w, y u, y v, y w, and then you just do like this row. Whoa, get out of here. What is up with it today? This row times that row times that row, and then minus the green rows. You guys remember doing that? Well, that's how we define the Jacobian for 3. You guys remember how the volume of a parallel pipette with 3 sides given by vectors is basically like u dot product with the cross product of the other 2, and that's basically what we're doing here. Okay. So our DVs can be squished a little bit and stretched. So we need this guy to kind of recalibrate when we do substitution, a UVW substitution. Okay. Let's see. What if we had this thing right here? And our region is x is from 1 to 2, x times y is from 0 to 2, and z is from 0 to 1. Then like we could do this transformation where we just make v be xy and w could be 3z. And so then if we do that, then what are the 3 inequalities turn into? So what is the inequalities around u and v and w? Yeah. So v would be 0 to 2. And u would still be like 1 to 2. And then w, I don't know. Maybe I don't like this. Maybe let's let w equals z. That makes it nice. We want to avoid fractions when we can. What's that? If they tell you to do a particular substitution and you want to do a different one to avoid fractions, you ought to get the same answer at the end. So go for it. Okay? So. All right, what's the Jacobian here? So my Jacobian gonna be, we've got XU. How did I do it? Yeah, X is down. XV, XW, YU, YV, YW. ZU, ZV, ZW. Compute that. It'll have a lot of zeros, which will be nice, right? Hmm. So in this case, you gotta solve for y here, right? So y equals v over x, but you want to have y only in terms of UVW, but x is just u, so y equals v over u. Right? So here, the x derivatives are just 1 and zeros, and the z derivatives are 0, 0, 1. And the only ones that are interesting are the ones involving y, right? Y has no w, so they have a 0 there. And then y with regard to u would then be like a negative v over u squared, and y with regard to v be, get out of here, 1 over u. Okay? So then, if you copy down the other two rows, the first two rows, then there's only one diagonal that has no zeros. So this diagonal has a zeros, this diagonal has zeros, this diagonal has zeros, this diagonal has zeros, and that diagonal has zeros. The only one that doesn't have zeros is this guy. 1, 1 over u, and 1. So the Jacobian is 1 times 1 over u times 1 is 1 over u. So this guy, this is the only diagonal. Let me erase the things I'm crossing out. Oh dear. So the one circle is the only one with no zeros in it. So your Jacobian's 1 over u. So that means when you substitute here, you're going to get an extra 1 over u. So then this triple integral, what goes on the inside? So every time there's a y, it needs to be a v, because that's the only one that mentions y. Right? So don't plug in all your u's first. Don't substitute all your u's first. Substitute your y, your v's first. And then pick up the pieces from there. We want to turn the inside into u, v's, and w's. Yeah. I keep touching that thing, right? And then there's a 1 over u, and then all the dv's and stuff. And then you can do your u is maybe you want to do your u on the outside, your v on the middle, and your w on the inside. And then you're off to the races. Yeah?
Rectangular. Does it matter where exactly we put our bounds? Like, do we have, a U on the inside?
Yeah, when you have all numbers, you can swap them out to your heart's content.
Convenience.
Switch them around as much as you want. Great question. Other questions? Okay. Let's think about switching to spherical. So in that case, x equals rho cosine theta sine phi. Y equals rho sine theta sine phi. And z equals rho cosine phi. So what's the Jacobian? We're switching to spherical. That's what we should end up with. But let's do it. So we'll do x rho, x theta, x phi, y rho, y theta, y phi. Maybe my computer's had enough of Calc 3. Okay, so it's back. All right, and then z rho, z theta, and z phi. And so then you've got, let's do these calculations. So then x rho, so doing all the rho calculations, you've got cosine theta sine phi, and then sine theta sine phi, and then cosine phi, and then x, all the theta derivatives would be negative rho sine theta sine phi and positive rho cosine theta sine phi, and then z theta would be 0, and then all the phi derivatives would be rho cosine theta cosine phi, and then rho sine theta negative wait, nope, positive cosine phi, and then negative rho sine phi. Right? And then you would copy the first two rows down again and off to the races as far as finding all the things, right? And so then, I don't know, you guys are not really excited to redo a calculation you already know, are you? Yeah. So what's going to happen is once you copy down rows 2 and 3 and start multiplying these guys, you're going to get lots of cosine squareds and sine squareds. You're going to combine those cosine squareds and sine squareds, except there's one thing that's not going to have, we're going to have a sine phi that doesn't get squared in some of the terms. So, yeah. All right. So I do want your homework.
Question where it said that the bounds are from 0 to 1x. I think it's a typo. And it should be 1.
In the homework or in the
Yeah, sorry.
which
5-4.
5-4?
It's really like it doesn't really work.
That's what Alex told us at least.
But I did do 1x.
5-4?
That's why I.
Which number?
It's office for 4 hours on Monday doing the wisdom, so.
It's supposed to be one? Yeah, I did that.
I don't know. All right. All right, but I will take your homework.
Right there. He prepares, be amazed. Absolutely. Average score is a. Well, maybe a 4 out of 47.
And then I would strongly encourage you guys, when you're studying for the final, to come to the math collaboration room, work on some problems on a whiteboard. Like just go through old homework problems and old exam problems. Those are some of the best things to do. If you only just read the textbook or watch videos, that's gonna be a lot of wasted time. The best use of time for studying is actually doing problems. Okay?
Nap time.
So they spread out their ways.